this, and this is T. Does everybody agree with this? That we have T here, we follow it around T, and we have T here. Okay? Okay. Karen, what about this cable right here?
It's 2T pulling.
2T. Does everybody agree with that? Because if we did a free body diagram of pulley 3, we have T coming down here, we have T coming down here. In order for it to be static equilibrium, this has got to be 2T. Okay, and now we have two pulleys. This is pulley 1 and this is pulley 2. And what are we looking at? We're looking at is this right? There's 2T here, right? We determined that's 2T. And then there's a cable coming out over here. So let's go back to our whole talk about the two different kinds of motion. What kind of motion is there? There's translational motion and there's rotational motion. And translational motion is what static equations, what static equilibrium equations do we have to show that something that was possibly moving in a translational motion is not moving? What would that be? So when we deal with no translational motion, what are our static equations that we're using? Right, some of the forces in the x and the y and the z is equal to 0, right? And that's all we've been dealing with so far is translational motion. But in statics, we're also dealing with no rotational motion, which on Tuesday we're going to start moving into. And in this case, if there's no rotational motion, I'm not using the sum of the forces equal 0 anymore. I'm using what? Some of the torques. And in engineering, we call it moments. So this is moment. And this is forces. And x, y, and z equals 0. So in this particular problem, I'm not just looking at forces, I'm looking at a possibility of a rotation. So here's my center point, let's call it point O. What did I say the dimension is of this first one?
1.
The diameter is 1, right? So this is a half. You know what, could I just change this to being the radius of 1? Just so we're using easier numbers. So this is 1 meter, and what's the radius of 2? 3 meters.
What's the symbol for radius? Star?
R. So if I do sum of the moments about point 0, Peter, are we up to you? You want to do that? Think of torques. So remember right hand or your right hand? So your fingers go in direction of the force. So I'm going to look at this 2T first. I'm looking at this guy. Putting my fingers in the direction of the force. My palm is going towards where I'm finding the moment about. And it's going to spin in the counterclockwise direction. So I want to multiply 2T times 1. That is the moment that's created about point O. And if this distance right here is 3, this is 3 too. So Peter, could you do this one?
Which one?
Do this one? So the sum of the moments for this, let's call this, let's use a variable that's not in here. There's no p's, right? Let's call it p. So it's p times what is the moment? 3. And it would be negative because now my fingers go in the direction of the force, my palm goes towards the point, and my thumb's going into the board. It's a clockwise rotation. So it's negative, equals to that. So 2T minus 3P equals 0. So P is equal to 2T over 3. And I'm going to write it a little bit differently. I'm going to write 1/3 of 2T. So Andrew's asking if initially I gave you a diameter of 1 and a diameter of 2, we would have to find what the radius is, and the radius is half of the diameter. Because the distance here, right, this is the lever arm for this force, so I would have to multiply it by the radius. So if the diameter was back to 1 meter, it would have to be a half. So I have 2T being, I'm lifting something 2T here. Is this giving me a mechanical advantage? So is the left side or the right side larger?
Left side.
The left side is larger. So where do you want to be? On the left or the right side?
Right.
You want to be on the right side. So notice the one that has the mechanical advantage is when it's going from the small pulley to the larger pulley. So I would want to be on the side of the larger pulley. So the pulley that's going around, where would you want to be? Would you want to be on this side pulling or this side pulling? On the larger side pulling, and it'll give you a mechanical advantage. Okay, so now let's go back to this problem. We had T, 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 2T. So what's this equal to here, Paul? If this is 2T, this is equal to?
2/3 T.
2/3 T. And then Yali, here we have our weight. What's our weight equal to? So I can draw a free body diagram. Draw a free body diagram of pulley, what is that, 4? So let's see, here's 4, right? This is pulley 4. We have T going up here. We have T going up here. And we have, what did we solve? 1/3 2T here. And we have to figure out how they're equal. So what's the weight equal to?
8T over 3.
So you add it all up, right? So it's 2T plus 1/3 T, 1/3 2T. So what's that come out to be?
8T over 3, I think.
8T over 3. So let's solve for T then. T is equal to 3/8 of the weight. Let me just make sure I have it solved for myself. Yeah, I don't have the answer yet. Somebody else got 8T over 3? So the tension, take a look at this whole problem. Here's the weight that you're trying to pull up. You're trying to raise this, and this is where you are. Do you have a mechanical advantage? What's T equal to? 3/8 of the weight. Do you have a mechanical advantage by pulling here? Yeah.
Yeah.
Because even though this weight is whatever, you only have to pull 3/8 of it. Okay? So these are the pulley problems, and there are some in your chapter homework. So pick a place to start from, and just use the rule of continuous cables give you the same load. And then if you need to draw free body diagrams, you can. It might help you draw it. Or if you do it all in your head, you just keep going, go, this is T, 3T, 4T, T equals W, da, 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 da. Okay? And in the homework, there are 4 plea problems.
Are we turning those in Tuesday?
Yeah, that's all due on Tuesday, so if you look at your homework,
They're included now, right?
yeah, it's all, the whole homework is due then.